Okay, so first want to mention that next week we don't have a class, but I will like try to make a record and I will send you the video link for the next week class. No, we have no physical class next week, but yeah. All right, so this is just a small refresher about last week we talked about spell equality. So and I remember that yeah, so just refresh that. So last week we proved that we discussed so-called this CHSH game such that if there's no entanglement between Alice and Bob, then the max probability that they can win for this game is 75%. And the proof is just very simple. And I show that if you have this spell inequality, or they have this so-called EPR pair, then they can win with 85%. And the proof is complicated. I just mentioned last week. So the upshot is that this CHS game very equality. Basically, if Alice and Bob share a single qubit of entanglement, then they can win more than 75%. So what is okay, and then this is strategy, and I mean yeah. So this is the proof. Why I talk about this CHS inequality? The idea is that so what this experiment and this inequality shows is that if you have if you are physically separated or spatial separated two parties, and you play with this game, then you can win more than classical probability. Basically, if your opponent can win 85%, classical can only at 75%. So what this story telling me is that if you have two quantum devices, then it's very simple for you to beat classical. You can just play the CFS game, so you can easily beat classical. And moreover, that there's a more exotic non-local game that says so for maybe square that quantum can win 100%. Classical can win can only win up to 17 divided by 18. And there's a more sophisticated game such that quantum can win 100%, but classical can only win negligible probability. Okay, so this story tells that if I have two quantum computers separated, one is on the Earth, one is on the moon, then you can be classical. But how about that you only have one quantum device? Let's say in the universe there's only one quantum device. There's no two or more quantum devices. Then is there any way that you can also give you some so-called quantum supremacy? And this is why starting from this week, then we will try to define a so-called quantum computation. 我用中文讲，就是说，你如果有两台量子的 device，一个是分开的话，那你可以你可以把 Bell inequality 变成一个游戏。那你在这个游戏当中 ，quantum 可以打败 classic。但是如果你今天只有一个 device 的话，你就没办法做到这件事情。所以你要 define 什么叫做量子计算。所以严格来说，从现在开始，so starting from now, we are start to learn what's definition of this quantum computer. And yeah, so this is just the proof. So basically, I think I remember that I just upload this PowerPoint. Yeah, so you can read the detail about this spell inequality and CHSH. Okay, so but before we talk about this, okay, yeah. So before we talk about this quantum computation, we need to go to some other small region called density matrix. This is not so related to quantum computation. If you don't know about density matrices, it should be fine. But I think this is somehow quantum one important part in quantum information, although it's not so related to quantum computation. So I would like to talk about this so-called density matrices formalism. Okay. So what's density matrix? Maybe you're there density matrices before, but usually the quantum physics textbook will not talk about it. So so the states that we talked before is so-called pure state. A pure state you can view basically as a vector in the finite dimensional Hilbert space. And what density matrices mean is that we want to mathematically define a system which represents so-called probability mixture of pure states. Okay, so mathematically, so we just write summation of I, pi, psi, psi. So this is so notice that this is not a number, but this is the operator. So this is the cascade roster. So what this equation means is that there's a system and you don't know, so you're not comfortable about what status of this system. So this mathematically means that there is a probability pi such that the system is stable. So this is the mathematical the equation looks like this, but its physical meaning basically is what I say is that so this system you have, let's say you have probability pi, a system, a resistance is okay. But mathematically we write it as this way. So for example, okay, and basically this can be pure classical statement, right? So for example, for example, if you have a bag and there's a black so if the color of the ball is black, let's say I use 0, and the color of the ball is white, then I use 1. And if I don't know, and there's a probability half that there is the ball inside the bag can be either white or black, then I can use this representation.
So is it the matrix so that if I take state and I left multiply with the matrix, I get a chance to get that state?
What do you mean? Here?
Yeah, so if that's the matrix,
yeah, this is
and if we take a certain quantum state and then we left multiply by that matrix, then we get a chance that this matrix, which is representing the multi-state, is that specific state.
Not exactly sure, because what you're saying is true if these they are all also orthogonal to each other. If not, it's not.
Oh yeah.
Yes, yeah. So mathematically we can just write this. So okay. Right, so yeah, so basically in this case it's true. Right? In this case it's just this.
Yes.
So yeah, but I can also write something very weird like this. So what this just means that we probably have that the state is at 0, we probably have the state is plus. So mathematically it's fine. It's a logistic statement. Yeah.
So but then if I only have the matrix, I cannot really reverse engineer out of which the second state is possible, right? Because there are multiple combinations of states.
Right, exactly. Yeah, so this is what I want to say. So density matrices doesn't repeat. The physical explanation is this, but this interpretation is not unique.
Yes.
So for example, this is 0, 0 plus 1, 1. Okay, so this is somehow like non-trivial, but we check proof is also this. Yeah, so one can also say that this system has probably have to be positive and probably have to be minus. The interpretation of this is not unique. 大家懂吗？比如说这个 state 1/0000加1/11跟1/1正加1/1负是一样。我说数学上一样。所以so mathematically this is yeah, this is identity. Yeah, so this interpretation is just it's one interpretation, but it's not a unique interpretation. Okay, so key question. So if I tell you the interpretation, then it will be trivial that you can arrange. But it's this. And the key question is that which matrices are valid density matrices? That's somewhat like inverse question. And basically, density matrix is a statistical mixture of pure quantum state. Okay, so the first, so this is a simple theorem. The theorem says that the density matrix is satisfied trace. Okay, so you view this as a matrices, right? So you can pick any basis. Notice that trace is invariant under basis. This is what we proved. There's some simple thing in the algebra. The trace rho is equals to 1. And this guy is a mission. And the rho is positive semi-definite. Okay, so this is the if you start from here, then you can prove 1, 2, 3. All right, don't worry, I will prove. And conversely, any d by d matrices with this property is density matrix. Yeah, so this is a theorem that okay, so let me see where the proof. Oh, okay, okay, yeah, there is a proof. Oh, maybe let me or I can go here. Okay, so the first one is first one is so trace rho, you just take the diagonal, right? So you just pick any basis A, also on the basis, then just sum over A rho A. Okay. And you just write your rho. What's rho A comes from? You pick any basis A, right? So you just do this. Let's say so the rho AA is basically A rho A, right? So this is the matrix element of rho. Okay. So just write A, I, T, I, and A. So notice that these are complex conjugates, so you get scales. Okay, so when you sum over A, sum over A, sum over A, okay. And you can exchange, let's say I sum A first, right? So I can I and PR is independent of A, right? Okay. And notice that this is basically, if you forget about, you just sum over I, and then you sum over A first. So you get this say psi I projecting onto A, right? Sum over A. So these are basically just the states normalized, right? So this is one. This is basically all the components squared. Okay, so you get sum over I PI. And this PI probability. Okay, so trace rho is 1. And permission is also simple because these guys are real and these are projected summation, right? So yeah, summation. Okay, simple proof. And so the rest is positive semi-definite, right? So in order to prove it's positive semi-definite, remember we are trying to prove that this side is greater or equal to 2. Okay, so we just do the same proof. So proof just write down the proof. Just over I, and phi I at the numeric square. Okay, just write down. So it's basically this. You can low it, you get low it. That's where you get 5, you get 5. Right? And these are at the value of square. And these are probability, right? Greater than 0, greater than 0, so sum over all the non-negative numbers, which are going to do. So rho is positive semi-definite. Yeah, these are just start from definition, right? Okay, so conversely, it basically asks about you give me any matrix rho which satisfy these 3 properties. Trace 1, positive semi-definite, and permission. Then I can always write rho in terms of this. Okay, and the reason is that since permission, right? So I can use this. So it's diagonalizable, so I can write a spectral decomposition as this. But up to this stage, I don't know whether I can interpret this number as a probability. But since that these are positive semi-definite, so all its eigenvalue is greater or equal to 0. And also since trace equals to 1, so these are these eigenvalues are numbers which are non-negative here, and then their sum equals to 1. So this means that I can interpret this state A with probability PA. Yes.
Is the trace invariant under basis?
Yeah, it is. Yeah, exactly. Yeah. This is using this identity. So remember that you have this trace AB equals to trace PA.
Oh yeah.
Right. So that means that if you change the basis, that means there's a unitary. So you get a new row, you taker. It's basically trace. You just exchange this with this. Yeah. That's okay.
Technically, we require it to be unitarily diagonalized.
Right. This is true. This is true for permission matrix.
Yeah.
Yeah. Okay. So this is a proof. But what is proof? Tell you that you can take any unitary and change the value. So the probability is invariant, right? Because the probability is eigenvalue of the matrices. The eigenvalue of matrices is invariant under a unitary transformation. But the eigenvectors, I mean, it's not this state is not unique. You can take any unitary and you will change the state. So the interpretation is not unique. Yeah, the simplest example, as I showed, is that 0, 0 plus 1, 1 is equals to plus, plus, and minus, minus. Oh, okay. Oh, good. Okay, so this is the density measure. So let me say again. So the physical meanings that the system is say A with probability PA. Or yeah. Okay. So in general, this density measure, this measure is in this kind of density measures, called mixed state. And one particular case reduced to the pure quantum mechanics is called pure state. So pure state is meaning that you're 100% complete sure that these states must be S state psi I. So simply speaking, pure state is just you can write these density matrices in terms of one particular state. Oh, so this reduced to for one, right? So this reduced to the original quantum mechanics. Okay. So this is the definition. And one non-trivial thing, probably is also trivial, is that if rho represents the pure state, if only if its square is equal to itself. Okay, and this is the equivalent to having one non-zero eigenvalue. Okay, so let me say again. So the pure state, the original definition of pure state is simple. You just say that there's no ambiguity, right? These states can be represented as psi. Okay, and but this statement is the same as the first statement. The first statement says rho represents pure state only if its square equals to itself. And actually we can prove it. So notice that if the state can be represented right as this, then obviously that rho square is the same as rho. Right? The reason is that so now it should be a simple calculation. Okay, we just write rho square itself, and this is 1. This is inner product. So now you see this bracket notation is amazing. Okay, so if any pure state if I write any state rho as this is projected and squares itself, right? True. Okay, so non-trivial part is that if rho square equals to rho, then it can always be written as this. And the reason is that there are various ways to see it, but one simple way is that let's say you write a state as this, and you compute square. Square. Then what will you get? Or basically, let me say this. So, uh, so I can. So when I write this definition, I didn't say that these states are orthogonal, right? But for if you give me tensor matrices, I can make it orthogonal. Just pick the orthogonal basis. So for rho, if I write as this, if I square it, it's easy to prove it. Just square it as this. Just square as the eigenvalue, right? Pi just go to pi squared. But pi is a probability. If it's if it's square, if you take probability square, right? Yeah. In general, it should less than pi unless pi is one or zero. Yeah, unless pi is one or. Right, so that means that if you square your density matrices and force this to be original, to be a same as original density matrices, that means that all the probability either one or zero. So for zero, meaning that there's no component. For one, there's only one component. So this means that if rho square equals to rho, then rho must be a person. So this is if and only if. Yeah. So more generally is you can easily show that your trace rho square will be just sum over pi square, right? So in general, that's equal to trace rho, which is one. And if you trace rho square is one, then if and only if rho is pierced. Although this is common. Yeah. So in general, if you want to show that, so you can just compute this guy. Trace rho square. There's a name for this quantity called purity. Yeah, basically purity is bounded as in zero one. And then if it's one, then it must be purest. And the thing rho square is equals to rho is the same as having one non-zero eigenvalue, which is one. So this is a simple calculation. So for rho, let's say you're a mixture of 0 and 1, and you can just write half of 0, 0. Oh, and amazingly that you can say this, let's say you have 50% of plus 1 square root of 0 and 1 minus its 1 square root of 0 minus 1. So you can just compute it. I mean it's not trivial, but you can just plug it into this. Then you will find that half of plus half of minus is the same as half of 0, 0. That's common. So that means the interpretation of this is not unique. Actually, by the way, these things are pure classical, right? Because I mean, but non-trivial part is that if you allow so-called quantum mechanics, there's a superposition, then there will be different ways to interpret these states into these. Alright, so I just say that these things are pure classical. So these statements just say that I have 50% of something plus 50% of something. But if you allow that quantum mechanics, you say that there's a plus state, minus state, which is a superposition between these two, then you will have different interpretation of original classical. Yeah, I mean still classical, but give you like it basically just a change of basis. Oh, okay. Okay, and by the way, so these are single qubit. These are single qubit states. So you can generalize this. You can think about this rho in terms of tensor product, which may be complicated. Okay, so let's say you have two parties A and B. Let's say you have two parties A and B, and then there are some qubit in A, some qubit in B. So basically, there are Hilbert space HA right here in the proton Hilbert space HB here, and you can study the density matrices on this whole system. Okay, so notice that the original state side right, in this A and B, the secure states, basically some combination with basis A and basis B. So A belongs to here versus the basis A and B belongs to basis B. But in terms of density matrices, you need to have four, like, you need to have the ground side of this A and B. Right? So which made it very complicated for bipartite state. So bipartite basically means there are two parties. So for two party states, that in general your rho AB can be written as some order A cross B cross rho AB right for this. And A and B. So these are cast state, these are graph state. But basically tensor product with just using the same logic, these are cast state, the tensor product, and graph state, and tensor product just combine all, and then get good. So
why do we now have the A and the A accent?
you mean what is different?
The A prime, yeah. Why do we have A and A prime now and not 2 times A?
You mean not like this?
Yes.
Last
one for the one, well, for the non-bipartite state, we had twice the same state, right?
So what? So what does it? So yeah, it's like this. So if you have a so notice that this density matrix is basically some number, right, and some state like this. So for the tensor product of A and B, right? So the general state should looks like summation of A and B, or some AB, right, and some number here for general two, right? Are you yeah? And so if you compute it broad, then you need to use some notation A prime B prime and some number A prime B. Right? If you start, so that means that if you combine these guys in terms of density matrices, then you will be sum over 4 indices.
Okay.
Yes. Yeah. Okay. That looks complicated. 对，有没有什么问题？这就是说，你如果给一个 state 的话，你可以把它，如果你有两个 party 的话，最 general 是可以这样写。对，是 A 的，so I use A prime B prime just tell you that, yeah, just to make sure there's no confusion. You know that this A prime is the dual side of A, and the B prime is the dual side of B. And so this is why in some textbook there are also used this superscript to say that there's a so that you know which Hilbert space you're dealing with. So, and there's a operation called partial trace. But partial trace doesn't meaning that I take a trace, but I just I only take trace on, let's say, system B. So if I don't take the trace for the whole space of the images, I only take the trace on the subsystem B. So physically, you can say that, oh, I just trace out. There's some you learn some like high-energy theory. They or some other theory, they have to say that, oh, so if you have a huge system and you only care about one particular system subsystem, then you can trace out. So mathematically trace out means meaning that you just trace out B. So this trace B is the same as what we define for general trace. Okay? So trace B, subsystem B, just take any orthogonal basis B, and you just compute B with something B. Okay, and you get another density matrix only this on A. Okay, so for the trace B, meaning that you just take B and B prime to be the same, and this will be different this. Okay, so that's it. I use C. So you just replace become A C A prime C, and then A prime. Okay, so you just remove this B and B prime. You got this guy.
It's a use B and B prime.
Yeah, I combine B and B prime, right? This is the same as trace. Remember the trace is basically the diagonal, but now a diagonal only on B. So I can say, oh, B and B prime should be the same, and remove it. So I get this. Okay, so now trivial thing is that this guy the density matrix is on A. If row AB is a density matrix on A and B. If row AB is a density matrix on A tensor B, then you pocket once you pocket trace it, then the remaining guy is a density matrix on A. Okay, and the proof is not simple, but yeah, so not a trivial, but so I just ignore it, but you can try to do this. And one might say, oh, this looks weird, right? But what else that this is covered. And this is exactly the same as in the classical probability theory. There's a thing called marginal distribution. I don't know whether you know it, but let me explain. So, I mean, I can connect this into marginal distribution. So marginal distribution is like standard thing in classical probability theory, right? Let's say in classical probability theory, you can say, oh, I have a probability which is joint probability distributed for variable x and y. And the joint probability and the marginal basically mean that, oh, I can define a probability that I only care about x. So I just do the possible, or maybe I use this. Let's say I only care about probability x equal to x. It's the same as the definition basically looks like this. And sum over all the possible y. 这个叫 marginal distribution， 这个好像高中有学过，就是你suppose you have a probability distribution depending on x and y, but you are only care about what's the probability that I only get x equal to something. Then it's the same as you compute x equal to something, and then you sum all the possible y. This is the marginal. And obviously that if this guy is a very probability distribution, then this guy is also very probability distribution. Right? So for example, this guy is also non-negative where sum is equals to 1. Right? Because that if you sum over x, we got probability x equals to x, and then sum over x and y, probability of x equals to x, and y equals to y. But this guy is a probability distribution on x and y, right? So this definition makes sense. It's a probability distribution that's now negative. Okay, so basically this guy, this is called classical marginal distribution. And if you pick your row AB to be, if you pick your original row AB to be diagonal, okay, so let me say this. Be explain detail. 就是大家也学过那个高中数学，有那个高中，就在高中数学有教过那个，就是把这个 joint distribution 可以把一个变数拿掉，就是看上一个。This is exactly the same as. So you can do partial trace somehow like generalization of marginal distribution. Right. So for example, let's say I can let me say this. Suppose it's A, B, A, B, right? It's A, go A, A. Right, so this is the general bipartite, the bipartite state. Suppose this row is diagonal. So diagonal meaning that let me say what I'm trying to say. Oh, okay. So if I start with row which is let's say I take so I can interpret this to the density matrix. I can embed this guy. So I can say that I have a state looks like probability x. So I can interpret I can use this interpretation. So what this interpretation is that the x, I put x in the first cubic and y in the second. So I can say that this row is you get x and y with probability pxy and sum over x. But you need to do like, yeah. So this is the crack. Let me what did I say this? Let me use this. So, sorry, I spend some time thinking about how to write this. All right. So what this statement is that what this statement is this is basically pure classical, right? I just turn this probability x to x, y equals to y to this into these density matrices. Good. So for this statement, what this density matrices mean is that you get x and y. You measure when you measure the first qubit and second qubit, then you get first qubit in x, second qubit in y with probability of px and y. And then px and y just this. So let's say I define this guy to be pxy. And now you can if you use the partial trace, definition, then if you use the partial trace definition, then you just remove this y, right? So actually you get something like this. Uh, uh, so this is so this state has a classical interpretation. But if you use that partial trace formula, then you just remove y and sum over y. So you get sum over y, pxy, and x sum over x. So now you can interpret these states as you once you measure the x, the first qubit, then you get x with probability of sum over y, probability of pxy, which is marginal distribution of this. So that means that partial trace is partial trace is generalization of this. Yeah.
So is it then true that the AB A prime B prime is the A prime times B prime?
I'll do it. I think I say again. I mean,
Again, like is the chance of having A B A prime B prime like the coefficient in the formula from above is that same as B A prime times B. Talking about the coefficients. Yeah, it's the row.
oh, okay. The coefficient is the same. So what it means is that you just exchange these two.
So what it means the coefficient in the formula. So it says BAB is some, and then it says row AB A prime B prime in the first line of this slide. That coefficient is that the same as row A prime times row B prime. If you write the matrix BA and the matrix BB, and then you would express it again in this form that we discussed in that. Do you know what I mean?
No. Yeah, but I mean we can start it.
I just mean if you take BAB, the matrix,
You mean a BAB.
no, I mean the matrix BAB.
Oh,
Or like row AB, whatever it's called, the matrix.
okay.
For the two spaces. Yes.
Okay.
And now what we are doing is we're calculating BA and BB from this matrix, right? So we are reduced to the dimension.
Yeah.
Basically. And then if I would like to write my new matrix again, like as in this representation, where it is a sum over the states A times P of A times the outer product of the state. Right. Then are those P coefficients So is it true that if you take the P coefficient BAA for your BA matrix and the coefficient for your
So what do you mean by BA? I mean, you can do that.
okay. So I just mean yeah, it's easier to write it backwards. So let's say you BAB, and then from this we want to derive
Rho B. Okay. Yeah, you have two.
these. And let's say I want to write this again as some as this.
Oh, okay. You mean that?
Then I'm looking at this coefficient, and then of course this is like this double sum of and then like this, and then I'm asking whether this.
Oh, so you have rho A and rho B, right? So my question is that so you have rho A and rho B. So how do you write rho B back into this? Because rho B is only dimension 0 is B.
So it was like talking about probabilities only. So the probabilities in the formula. Is this true? So this is a probability in this formula, and this is probability in this formula.
No, I think so. If there are diagonal, then in this case, but in general, it's not. In general, it's since once I write this rho AB, right? This rho AB prime is not. This guy is not a probability. If I want to write this guy, if I want to interpret this into probability, then I need to somehow like diagonalize this rho AB onto tensor A. So then I can interpret this rho AB in terms of this. So this is why in this case, then I can right. So notice there is only two indices here, but there are four indices. So if you start with this rho, right, somehow like if your rho is a larger whole matrices on A tensor B, then you can diagonalize this rho in terms of this. Now you can interpret this guy as a PXY, as a probability.
Yeah.
So then you have this story that if you trace out, you get margin. Yeah. But in this form, it's not.
Oh. Okay.
Yeah. Actually, in this form, this number can be complex. I mean, this form can be complex number. Yeah, thanks. So yeah. So hopefully this example will tell you that it's classical distribution. Okay. 我讲一下，我懂的，就是说这个大家知道在说，就是说你如果把原来这个 partial trace 这个行为把它拿掉了，把它就听起来会不会诡异啊？我第一次听的话，但如果你把它想象成是 probability distribution 的话，就变成 partial trace 就变成是 marginal distribution， 就是你以前就是把其中一个变数，对，就是或者你在积分的时候可以把其中一个变数积掉，就是类似这个行为。所以hopefully this will make you feel that this partial trace is not yeah, okay, so we will see this example. Okay, so this example looks weird, but it makes sense. So let's say you take a bell pair, right? You take a bell pair. You take a pure state like this. This is bell pair, right? It's pure state. It's pure state A tensor B, right? It's a pure state. And you can compute density matrix. So notice that density matrix is 2 times larger than your state, right? Because now this state is dimension yes, 2. But if you write here density matrices, you get 4 by 4. Very simple. Right? The reason is that these are 4 by 4. So you can write density matrix as this. Yeah, hopefully it is, but I mean, for example, right, so notice that one can write 0, 0 as 1, 0, 0, and then 1, 1, and 0, 0, 0, 1 in terms of dimension. Okay, so 0, 0 for the cat, so the cross there, which is 1, 0, 0. Okay. And this 1, 1 is basically 0, 0, 0, 1. So if 0, 0 is a matrix computation, right? It's matrix of this. As a matrix product, you get 1 and there are all zeros. And for the 1, 1 and 1, 1, that 1. Okay. So if you use, also you need to compute the product term, right? But the product will give you of diagonal. Yeah, so this is the density matrices for this guy. This is a first thing. This is a first thing. So this is a first thing. Okay, so let's say you can you can trace over B. Okay, it's not trivial, but you can try to trace over B. That maybe write the truth. So the row is basically if I don't use matrix representation, I can just write as this. 0 plus 1, 1, and also is 0 plus 1, 1. We can have a 0, 0, 0 plus 0, 1, 1. Okay. This is the matrix. This is the bracket notation for this density matrix. This is the pure state. Okay. This is the and then so now you can tracing out over V. So mathematically tracing out just the definition, but physically you can basically it's a state which Alice only observed from his part. Because Alice cannot see the bar part, right? So the whole physical state for Alice is just row A. Right, so you can try to compute. Okay, it's row. Let's say it's row A. And how do we compute this? Okay, so we're some so it's difficult, but we only care about this, right? Because you need to delete. You need to delete B, right? So if you do a trace B, you basically sum the state which is B is the same. So yeah, you only get 0, 0 and 1 and 1 with the same magnitude. You get 0, 0 plus 1. Because your partial trace B, right? So these guys there's no contribution, and then these guys no contribution because they are not the same. So you get this. The first one is the first. You get this one. I mean, it's trivial that it must be 0, 0 plus 1, 1, but it has, right? Because there probability somewhat. In terms of matrices, it's just this. Okay, but what's the physical meaning of this equation? So so this is exactly the same as probability of half. You get 0, probability of half, you get 1. So basically, but this matrix is just this density matrix physical meaning is just random. I just say that I have a coin. Then I have that probability have to get tail, probability half to get head for this thing. So what this means is that if Alice and Bob here, and then there's a Bell pair. For Alice view, her qubits is basically for Alice, right? Her qubit system for her is basically like complete random. There's no information here. Because the partial trace of row A is the same, it's complete here. Then this physical meaning is that I get probability half for my state to be 0 and probability half to my state to be 1. This is nonsense. This is the same as I have a coin. And I get probability half to be head. Probability have to be tail. So that means that Bell pair cannot transmit any information for Bob, for Alice, or similar for Bob. So for the Alice side, her qubit is the effect of her qubit for her is basically just a subclassical coin, some coin. They're also similar for Bob, but for the third guy who's here, which play the CHS again and Bell inequality for this guy, this third guy will find some non-trivial correlation between A. So that means that, so this also answers your question. So the whole density matrices cannot be reconstructed for two parties because we know that there's an effect here. So that this is why there is a Bell inequality. But for either rho N and rho B, for Alice and Bob, their density matrices are completely trivial. Because their density matrices are completely trivial. They just got some classical coin. But for the third guy outside this system, he can play this Bell inequality so that he get non-trivial results. So yeah, so this is the real problem. So that means that you cannot reconstruct original density matrices from A and B itself. 我再讲一次，就是说这个算完之后，你会发现说，这个 Bell pair，这个 Bell state 呢，你把它 partial trace 完之后呢，你得到的，你在 A 这个点得到的 A 这个系统得到的 state 是1/2的00加1，那就是1/2的几率这个 state 在0，1/2的几率这个 state 在1。啊，这个是废话，这个跟你有一个硬币是一样，你的硬币有1/2几率是正面，是反面，就是一个，就是没有任何资讯，是废话。所以这个 state 呢 ，partial trace 完之后，在 Alice 的角度来说，这个 state 看起来是 non-trivial 的，因为有 Bell inequality，所以确实有东西，某一种东西在 A 跟 B 之间是有关联，所以他们才能打败 classical computer，得到更高的胜率的 probability。可是对 A 而言，他看到就是一个空眼，他没有得到资讯。对 B 也是，所以这个 density matrices 的总体并不能被个别的 density matrices 重新复制出来。等于是说 Bell pair 不能传递资讯，但是产生了 non-trivial correlation， 所以第三方会感受到 A 跟 B 之间有某种作用力，可是 A 跟 B 自己不知道 ，A 跟 B 自己不能感受出这个东西。
也有嘛，换出来啊，点的作用力。
哦，没有啊，就 A 看到就这样，对 A 而言他看到，然后 B 也是，所以只有站在外面的人用 non-local game detect 他们两个之间的作用。对 A 来说，他没有办法知道 bug 是不是有跟他有 correlation， 对不对？对，因为 Alice 看到就是这样，就算今天没有 bug，Alice 自己有一个 qubit， 他看到也可能是这样。所以 for Alice， 在 Alice 的世界当中，它跟有一个硬币是一样的。可是对外面的第三方而言，看到就却不是这样。
这个 case 的前提是它是 pure state，
就一开始有一个 Bell pair pure state share with Alice and Bob，but for Alice side， 因为 Alice 不知道他看得到 Bob。当然你可以，当然有一个问题是说，那你怎么知道 ？So there's an additional question that how Alice how that one knows there's a Bell state, right? So this is why we need this non-local game. Because if they win with more than 75%, then there must be entanglement between A and B. So this is why Bell inequality got Nobel Prize. So this is why it's important. I mean, you can think more, yeah. Oh, okay. So in quantum mechanics, that remember, so this is state, right? So in the quantum mechanics, there are three axioms. One is the state, another second one is the unitary transformation. We say there is to transform one state to another state, you need a unitary. Yeah. So we need a similar axiom for density matrices, right? So we need to say, oh, what about I pick some unitary and apply on density matrices? Right? Okay, so this is a rule. So rule is say that if I give you a density matrices and you apply unitary, and after this unitary, the state is just this. You will take. And for a state, you just unitize the state, right? But for density matrices, since there are cat and ground set, so you need to have U and U there. Oh, okay. So if you see carefully, this is the reasonable operation. The reason is that remember that after this operation, the state must still be density matrix, right? So this guy must have trace 1. So this is why you need U and U data. So you get trace 1. You preserve the trace. And also positive semi-definite, also the permission. So this is the reasonable expression. 我意思是说，大家如果直接看会觉得第一次看觉得就很奇怪，为什么要两边都 把它都夹起来。但是原来在 say 的时候，你只能拍在一边，但因为现在有另外一边，所以你要配个 u deck。但是数学上来说，这是自然的行为，因为你必须 map 完之后还是 density matrices，所以这个家伙的 trace 要是一，然后它是 positive seven density，然后它是 permission。So permission positive and seven and the trace equals to one. This is the reasonable expression. And so mathematical, so physically, you can say that you just very simple. You just transform psi I to psi I with probability p. Oh, hopefully. So this is just the definition. You can see that you can view it as a definition. Okay, so what's the third one? Right. So third axiom is measurement. Right. We already talked about state and unitary and measurement. And so for density matrices, we have the definition and we have the unitary, and we are left with the measurement. And this is complicated, the most complicated. So, okay. So statement. What statement is that? So if you take any projector, let's say pi I. So remember, the projector basically is the same as the quantum mechanics. If I get the same as your quantum mechanics, right? Your quantum mechanics take some measure something to the diagonal and the projected eigenvector is the same as these formulas that you get the projector. Then the probability you get I is the trace of pi I mu as matrices. So these are matrix product and detect trace. I think this formula is common in like statistical mechanics. In the statistical mechanics, then you know there is a trace, right? There is an equation for the trace matrix type law. So this is the probability. And the post measurement state forget outcome I is this. This is complicated. So if you forget about this, because sometimes I forget about it.
Can you write out an example for the first equation?
Yeah. I can for example this one. This one. I can. So okay. So I first explain why this is or at least their physical meaning is consistent. So remember that okay. So remember so if you take a projector I, and then if your state, let's say your state, and if your state is psi or pure state, then what's the probability that you get this? Right. So remember that the probability of you get I, you get alpha. It's basically okay. So you can view a projector is that if you're studying compound mechanics, you can view a projector is the eigenvector of some permission matrices. Let's say not that number. Right. And you know that the probability you get outcome I is you need to expand this in terms of eigenstate and take the coefficient square. Mm-hmm. This is the same as you compute this like this, right? And this guy you can I mean I can write as this. Good. Mm-hmm. And I can so let's say this is pi. Let's say I use delta. I think it's fine. So this is psi or pi. This is the quantum mechanics statement, right? For quantum mechanics, let's say it stays pure, then the probability you get eigenvector lambda is this, right? You take the f, this is 7, you compute over that. But but now you can run this down as a projector. Okay, this projector. Okay. Okay, right? Okay, so if you believe this is true, then what the what? Yeah, but okay, so yeah, so the idea is that if I tell you that density matrix, the interpretation of density matrix is that there's a probability pi such as say this is psi I. So you have this kind of statement. Then Okay, so mathematical is this stable, right? But the physical meaning is that there is a okay, so probability EI for state psi I. So that means that you get probability outcome lambda for these density matrices to be linear sum of this with probability pi. And this makes sense, right? So you can. So whatever you get outcome I or outcome lambda is basically now you have some I. It's okay. Psi I. Oh, lambda psi I. Pi. This is reasonable. This is I mean, okay, so I mean, mathematically you need to it's not easy to see, but physically it's correct, right? Because for pure state, I get lambda with this factor, but this system will be this pure state with probability pi. So this is reasonable expression. 就至少觉得有。Okay, so non-trivial part is that this is the same as probably not so great stuff. So it's obvious. This expression is this. 这个是有没有一眼看出？然后没有写。Okay, so I mean that so it's here is it. Okay, so let me just write down the proof. So what is so that's so I want to so now I want to prove this guy is this guy. So that's reasonable. Right? So I want to, so this comes from the physical interpretation, and this is what I tell you. So these two must be the same. Okay, so let me just compute this. So you need to, all these combinations are just simple. Just need to write down the definition. So we start from here, and they say you take whatever. Say, they say I can J, or I say. Okay, start from definition. We just plug this row. Please. Right. So this is I just write down the definition. I plug this row into this. And I translate this. Okay, so now but this is sum over I, right? So I can remove it. Okay, so final formula is weird. This guy, psi I for projector is the same as this. Okay. So let me just hopefully this is the final thing we do. Oh, so there's a lemma. Let's say there say the trace of. So you this as a matrices. This trace this is as a number, right? This guy's a number. So arbitrary state and matrices. I claim this is true. Why? Why? What is? There's someone here. And say I take on the model basis. Okay, so I can change the order and use the orthogonality relation. So so I connect this is true. If this statement is true, then I can replace this guy. I can replace this guy to this guy. Then I prove the results. So the remaining is to show this is true for given any matrices and any state. So this is a matrices, right? So you take trace, you become number. This number is exactly this expectation value. And the reason is that if I trace using a definition, right, I think also normal basis J here, J psi, I can exchange the order for this expectation value and J here. And then now you can see our sum over J, but it's JJ. So these guys, the resolution identity. So I guess sum over J here. So this is 1. So we get, I guess, psi projector sum. Okay. So this is a proof. 有点复杂，我讲一下，就是说，因为你可能会看在其他课本上，我看到要写这个 statement，这是不是一秒？一秒我可以看出来，就看清楚。这意思是说，如果我说 density matrix 有一个物理意义，是说你得到 probability p， 你的这个系统在 probability pi 的时候会得到 state psi i 的话，如果这个 statement 是对的，那我得到 outcome 就是应该是这个 statement。这就是说，因为我在如果系统是 psi i， 我得到浪达的几率是这一个。那如果系统有 probability pi 存在 psi i 的话，那它得到浪达的几率就是线性叠加的自然的 physical meaning 的结果。OK，so the remaining 就是剩下就是说你去证明说这一个家伙这个 statement 这个是式子，它有一个计算的方式，就是你横着矩阵乘上多少 OK， 那剩下的就是一些有的没的计算，就是你把它写下来就可以了。OK，so yeah, so this is somehow complicated, very complicated. I mean, the proof is you need to think about it, but yeah. So hopefully this explain why this is true, because physical meaning. And the non-trivial part is the proof that this guy is true. Okay, so you can also prove this by using the same argument, because you know what's the state after you do the measurement. So you can combine each part and then recollect it back into a density matrix, and you can try to prove this. This is somehow like more complicated proof. 然后我讲一下，就是说前面这个证明只是说我得到那个 i 的几率是这个嘛，这可以证明，因为反正我有定义。那我也可以得到下面这个，因为我可以说这个 state 存在在这个 state 它是 psi i， 这个 psi i 变成是 outcome for state. So basically, let me see where is it? Oh, okay. So I didn't prepare the proof for this, but I can prove next time. Yeah, I require more complicated, but you can. Oh, let me just using words or sketch. Sketch. So I know the system, right? So mathematically, I know that the system has probability pi to be the state psi i. So once I do the measurement, then for this psi i, right? So I know there's some probability that then we just prove this probability I. Oh, it's not. It's an A for probability. I get outcome A. So after I get outcome A, the state will be. I need to use two instances. For state psi I, after I get outcome A, then the state will be psi I A. Right. So A becomes the basic projection. Right? With probability of this is actually also double here's the probability of A and I. Depend on I and A, right? Now, if I know this, then I can recollect it back into density matrices. So I can say after my state, so my state after the measurement will be the state in terms of this. With probability that pi times this and do some computation. So you guys say so. Probability of AI. Basically, yeah, and you need to collect. So if you do the whole computation of this, yeah, you spend some time in the proofs. So these are basically so you can do this axiom is basically derivable from you can prove it by using the quantum mechanics. The original axiom. Okay, these are not important. Okay, so maybe we take a 10 minutes break. Yeah.